Okay, let's dive into this. Welcome to the Explainer. Today, we're going on a seriously fascinating journey. We are tracing the path from abstract mathematical theory all the way down to hardcore bare metal C programming optimizations. We're getting right under the hood of hashing, figuring out exactly how modern software translates everyday, human-readable text into lightning-fast memory addresses. To get us there, we've got a pretty solid roadmap. We'll decode the hash function, look at the math behind Horner's rule, check out some wild speed hacks and bit shifts, see how to spread bits for maximum entropy, and wrap up with compression and collision resolution. Let's kick things off with Section 1, decoding the hash function. So here's the universal challenge, right? Finding data incredibly fast. To do that, we need a way to mathematically process strings, like a user's name or a password, and turn them into raw numbers. Enter the polynomial hash code. It's a method that uses multiplication by different powers to evenly distribute the influence of every single character across the resulting number. As our source material perfectly puts it, the core mission is getting a good spread of the object X with respect to other keys. I like to think of it kind of like baking chocolate chip cookies. You absolutely do not want all the chocolate chips clumped together in one single bite while the rest of the cookie is just plain dough. You want a perfect even spread. Same thing in hashing. We want an even spread of data across the computer's memory to avoid clumps that would just completely bog down our systems. Moving right along into Section 2, the math, specifically Horner's rule. So how do we actually compute these complex mathematical spreads without slowing our CPUs to a crawl? Because mathematically, a hash code is really just a polynomial. But evaluating it the standard way, that requires massive computationally expensive multiplication. This is where Horner's rule comes in, and it's a total game changer. By cleverly factoring out the variable a and nesting our additions and multiplications, we drastically cut down the total number of operations required. It makes the math incredibly fast to execute. But you might be wondering, what exactly is that variable a we're multiplying by? Well, theorists have actually run the experimental studies on this. They've tested and proven that certain constant numbers just work best for preserving information and giving us that good spread. The magic numbers, 33, 37, 39, and 41. Sticking to these specific constants makes sure that the low-order bits of our characters have a real, lasting impact on the final hash. Now here's where it gets a little crazy. As we multiply and add these values up, the resulting number grows extremely fast. So fast, it actually exceeds the finite bit limit of a standard computer integer. It overflows. In everyday programming, an integer overflow is a total disaster, right? It's a bug that crashes your app. But here, it's absolutely a feature, not a bug. We happily ignore those overflows. We literally just let the numbers wrap around, because doing that maintains our blazing speed while continuously churning and mixing the data for an optimal spread. All right, on to Section 3, speed hacks and bit shifts. Let's shift our focus to the relentless pursuit of hardware efficiency. Remember those optimal constants we just talked about, like 33? Well, multiplying by 33 is exactly the same as multiplying by 32 and then adding 1. But here's the thing. Standard multiplication is notoriously slow at the CPU hardware level, so programmers do these intense bitwise gymnastics just to avoid it. Since 32 is a power of 2, specifically 2 to the power of 5, we can simply take our binary bits and left shift them by 5 spaces. This left bit shifting is a lightning-fast hardware hack that completely replaces slow standard math. When milliseconds matter at scale, programmers will literally do whatever it takes to skip the multiplication table. Let's actually look at how this translates into real C code. Before we even process a single character, we initialize our hash with a massive prime constant. It's a classic FMV1A style initialization. Why do this? It gives us a highly randomized starting point, meaning even super short strings are going to produce complex hashes right out of the gate. From there, we jump into the main loop, processing every single character of our data. It breaks down into a tight 4-step process. First up, we use an XOR operation to blend the current character right into our running hash. Second, we hit it with that speed hack, multiplying by 32 by left shifting the bits by 5. Third, we combine this with a right shift of 59. That's 64 minus 5, by the way. This creates a cyclic shift hash code, which basically ensures bits don't just fall off the edge, they wrap around. And finally, we take the most significant bits and combine them with the least significant bits, using another XOR operation. This tight little loop is Horner's rule and our bit shift speed hack perfectly merged into pure, optimized machine code. Moving into Section 4, spreading bits for high entropy. Okay, so the loop finished processing every character, but our job isn't quite done. We still need high entropy. We take our 64-bit generated hash and run it through a finalizer function called spread_64, which hits it with even more XOR and right shift operations, specifically shifting by 32 bits this time. We are essentially squeezing out every last drop of entropy here by aggressively mixing the upper half of our 64-bit integer with the lower half. This guarantees the final number is wildly unpredictable and totally unique. Which brings us to our final section, Section 5, compression and collision resolution. So we've generated this massive, highly randomized 64-bit number, but eventually it has to fit into a finite array with a strict size limit. Normally, you'd use the modulus operator to find the remainder and make it fit. But check out this #_compress logic. There is absolutely no modulus operator being used. Instead, developers simulate it. They divide by the limit, cast it to an integer to drop the decimals, multiply it back, and subtract. Once again, they are finding alternative arithmetic paths just to squeeze out maximum CPU efficiency. But let me just pause and ask you this. No matter how flawless our math is, how fast our bit shifts are, or how high our entropy gets, what actually happens when two totally different inputs inevitably spit out the exact same compressed hash value? Well, that scenario is what we call a collision. It happens when a new element hashes to the exact same value as an element we've already inserted. Now, the absolutely crucial thing to understand here is that a collision isn't a failure of our math. It's simply a mathematical certainty. It's a structural conflict that we just have to be prepared to resolve. And the go-to fix for this is called separate chaining. Instead of letting new data destructively overwrite the old data, every index in our hash table simply holds a linked list of items. If a collision happens, no big deal. We just add the new element to the list at that specific index and traverse the chain. Zero data gets lost. It's a super elegant way to solve the collision problem while maintaining all that hard-earned speed we built up in our C code. So we've traveled all the way from the sheer mathematical elegance of Horner's rule right down to the gritty hardware-level bit shifts in C that make our modern digital world run so fast. And I think it leaves us with a pretty provocative thought. If something as basic as standard multiplication is considered too slow for modern hashing, what other invisible hardware-level shortcuts are secretly powering your favorite apps right now? Keep asking those questions, keep looking under the hood, and we'll see you in the next explainer.